Rosen, Discrete Mathematics and its Applications, Section 10.5 on Euler and Hamiltonian paths in circuits. Here we discuss Hamilton paths in circuits. And the difference between these and Euler paths is that Euler paths contain every edge in a graph. Here we are only looking at paths that contain every vertex once and only once. All right, so the mathematician Hamilton invented this Icosian puzzle, and it consists of a dodecahedron, and it has a peg at every vertex, and it sort of roughly approximated a globe, and a string was used to plot a circuit along the edges of this dodecahedron to see if it could be stretched to visit each of the 20 cities exactly once. And here's an illustration of that dodecahedron. It has bases that are pentagons, and there are 12 of them. All right, so we can express this as a graph if we take this dotted line, the back part of the globe, and we stretch it out and create where the back sort of is expanded like this, and the front of the dodecahedron is shrunk to be this front here. Now we have a graph model of our dodecahedron. And does it have a Hamilton path? It does. And this is one solution. It says the solution, but there's several solutions for a Hamilton path on this graph model of the dodecahedron. And you can see that it touches every vertex once and only once, and it returns back to its starting point to make a Hamilton circuit. All right, so that's really the definition, is a simple path in a graph that passes through each vertex exactly once. It's called a Hamilton path. And if it returns, if it's a circuit that does so, it's called a Hamilton circuit. And if it starts at x0, that's a vertex. The start vertex ends at xn. It's called a Hamilton path if the starting and the ending are not the same. And then Hamilton circuit if they are. And here's a few graphs. Let's see if we can see which has a Hamilton circuit or if not a Hamilton path. Fairly easy to identify in G1, a Hamilton circuit. We just go around all the vertices and get back to vertex A. G2 couldn't have a Hamilton circuit because of this, what we call a leaf structure here, but we'll start at A and we'll be able to make a path through every vertex. Well, G3 won't be able to make a circuit nor a path. We can make a path like this, but anything that has 3 leaves could not possibly have a Hamilton path. So there's solutions to a Hamilton circuit and Hamilton path for G1 and G2. And what can we say about Hamilton circuits and paths? It turns out that we do not have any necessary and sufficient conditions for a Hamilton circuit. About the best we can say is that the more edges you have, the greater the likelihood of being able to find a Hamilton path or circuit. So there are a couple of theorems related to the sufficiency for finding a Hamilton circuit, and they relate to how many edges are in the graph by discussing the characteristics of the degrees of the vertices. This first one is due to Gabriel-Dirac, and it says that if the degree of every vertex is greater than or equal to n over 2, I would have n greater than or equal to 3, then the graph will have a Hamilton circuit. So the more edges there are, you can build up to having the degrees be, in each case, greater than or equal to n over 2. A slightly stronger theorem due to OR is that if the sum of the degrees of any two vertices that are not adjacent is greater than or equal to n, then there will also be a Hamilton circuit. So if anything satisfies Dirac's theorem, it will also satisfy Orr's theorem, but there could be some graphs that satisfy Orr's theorem that don't satisfy Dirac's theorem. By the way, Dirac is not the Dirac of quantum theory fame. It turns out that it is his stepson, but quite an accomplished mathematician and graph theorist. All right, let's say a little bit more about Hamilton paths and circuits. First of all, that the complete graph with three or more vertices always has a Hamilton path and circuit available. We can always get from every vertex to every vertex because every vertex pair has an edge for the complete graph. But in general, the best algorithms for finding a Hamilton circuit or path for a given graph or determining that one doesn't exist have exponential worst case complexity as a function of the number of vertices. And indeed, the problem is known to be NP complete. So the problem is considered to be intractable for larger and larger graphs. How might they be useful? Again, anything where you have a model where you're trying to talk about places where important conduits intersect, like a utility grid or road intersections or circuits, then a Hamilton Hamilton path or circuit type of analysis might be important to you. In particular, the famous traveling salesperson problem, which is dealt with in our textbook in section 10.6, which we don't cover in this particular class. Ask for the shortest route that visits each city. So that's a Hamilton circuit that has the shortest length of edges or weight of edges. There is another example given in the textbook that called gray codes, which uses Hamilton circuits to try to reduce errors in certain types of switches. And I'll talk about that next. So here we have on the left a kind of a model of a switch where I'll star the switch model and the dial values for each one. So the dial values for this dial go from 0, 1, 2, 3, 4, 5, 6, and 7. And you can see that their values are labeled with the binary. And we use these binary values to indicate the switches. So this would have 0, 0, 0. This would have 0, 0, 1, where the middle row, interior row is the left digit and the exterior row is the right digit. Notice though, as we go around this dial, there's places where our dial crosses three boundaries at once and in some cases two boundaries at once, giving potential for more opportunities for error as we go across those boundaries. So the gray code type of dial would would order the values differently. So this would be 0 and 1 and 3 and 2, and this would be 6 and 7, and this would be 5 and 4. But note that each of these only differs in one bit position each time. And that reminds us perhaps of the Q sub n graph where there's 2 to the n vertices and they are connected with an edge with where their labels differ only in one value for their binary label. Turns out a Q sub n graph always has a Hamilton circuit, even though it doesn't satisfy Dirac's or Orr's conditions. And here we have the physical model of our gray codes, where we can see that we only are crossing one boundary every time we change values of the dial. So those are some applications and discussion of Hamiltonian circuits and paths.